Okay, this is a pre-recorded version of exponential functions review. So an exponential function is in the form y equals a times b to the power of x, where a is not equal to 0, a is greater than 0, and b is greater than 0. So let's start by just going and looking at one of these. So here is the equation. This is the equation. Y equals 2 to the power of x. 1 times 2 to the power of x. And what I'm going to do is I'm going to add in another expression, which is going to be a bit off the screen, but it's y equals a bracket b bracket to the power of x. And I'm going to add sliders for a and b. And let's start off. B can't be 1, so let's make b 2 as well. And we can see that the a value, when a is 2, a is 3, 4, the a value is 5, the a value is 6. So the a value is our y-intercept. Okay, let's make a note of that. A is the y-intercept. I'm going to go back to the graph. We're going to change the value of b. So, first of all, sorry, let's change a back to 1. So these, whoops, there. And b to 2. There. So these graphs are on top of one another. As the b value increases, you note how the graph gets steeper. So there b is 3, then 4, then 5, and so on. So as the b value gets larger, the graph gets steeper. As the b value, take it back to 1, or sorry, 2, as the b value gets less than 1, and almost there, then we notice that the curve becomes decreasing instead of increasing. So this curve here increases as we go to the right. The end behavior is from quadrant 2 to quadrant 1 increasing if b is greater than 1, and it's from quadrant 2 to quadrant 1 decreasing if b is less than 1. So b greater than 1, it's from quadrant 2 to quadrant 1 increasing. And if b is between 0 and 1, it's quadrant 2 to quadrant 1 decreasing. And what do those look like? Increasing function and decreasing function. Y-intercept in both cases is a. So, where do we want to go from here? What if, I'm just going to set something, I'm going to pause and set something up here. Okay, here's a graph here, and we're going to try and figure out what the equation of this graph is. So looking at this point, the y-intercept is 4, so we know that this will be of the form y equals 4 times b to the power of x. And so we need some more information. And what else do we have on this graph? So I'm going to try and find a point on the graph, albeit not very successfully. Okay, I'm going to click that off. So let's look for another point on the graph. Oh, there was one. 236. So we have the point 0, 4, and 236. So let's go back to here. Let's scroll this down a bit. Let me find my cursor. So we have the point 2, 36, and 0, 4. We know the equation is exponential, so it's of this form. We know that a is 4. And in this case, we know that when y is 36, x is 2. This is the point. X is 2, y is 36. Let's divide both sides by 4. We get 9 is b squared. B is plus or minus 3, but since it's exponential, then b is 3. And so this graph here has the equation y equals 4 times 3 to the x. So we're using points on the graph, this one to calculate a, and this one giving us an xy value which we can substitute in to calculate the value of b. Also, for every exponential, we know that the domain is a set of all x such that x belongs to the reals, and the range is the set of all y such that y is greater than 0. Okay, no equal to, strictly greater than 0. This curve will never touch down. It will get close to the x-axis, but it will never touch the x-axis. End behavior is always from quadrant 2 to quadrant 1, and as we said before, increasing or decreasing. And those are the characteristics of the exponential function. Okay, let's solve an exponential equation now. We'll do that by algebraically by expressing these powers, the 4 and the 120. Well, first we'll start by changing the square root of 128 to exponential form, which is 128 to the power of 1/2. Now, we need to express these both with the same base. So common base for 4 and 128 is 2. 4 will be replaced with 2 squared, and that's raised to the exponent x plus 2. And 128 is 2 to the 7th. We have power to a power, so we get 2 to the 2x plus 4 equals 2 to the 7 over 2. Again, power to a power, so we're multiplying. Since the bases are now the same, we equate the exponents so that 2x plus 4 is equal to 7 over 2. 2x will equal 7 over 2 minus 8 over 2, since 4 is equal to 8 over 2, right? 8 divided by 2 is 4. 2x equals negative 1/2. I need to divide by 2, but since I'm dealing with fractions, I'm going to multiply both sides by 1/2. And these guys cancel, leaving me with x is equal to negative 1/4. Okay, so we have x is negative 1/4. Now, if the test is over and I have time, I can verify this. So I can go 4 to the power of bracket negative 1/4, 4 to the power of negative 1/4 plus 2. Hit enter, and I can also do the right hand side, which is the square root of 128. And those are the same, so I know I have solved this correctly. But again, any verification like this will be done at the end of the test, not during the test, or you could find yourself running out of time. Okay, let's solve this one. Now, we can't express 6 as a power of 2, so we're going to have to do this graphically. So in y1, whoops, I was in the right place, we will graph 2 to the power of x plus 5, x plus 5. And in y2, we will graph 6 to the power of x. And let's set a window. We know that, well, we can go, let's try negative 5 to 10 is fine. And we know that the minimum y value we can have is 0. And let's try y max is 10. Let's hit graph. See what we get. Okay, I don't think I'm quite high enough in my window on the y, so let's take y max and let's make it maybe 100. And we'll go by tens and graph. So there's 2 to the x plus 5. And here comes 6 to the x. Still not quite high enough. So let's go a little bit higher, or a lot higher. Let's go to 200. And we'll go by, let's go by 50s, let's say. Again, here comes 2 to the x plus 5. And here comes 6 to the x. Still not quite high enough. Let's go to 300. And graph again. There we go. So somewhere right around here, second calc intersect. I'm going to move about to the point. I think that's close. Enter 3 times. And we get x equals 3.15. So rounded to the nearest hundredth. If we were rounding to the nearest tenth, then it would be 3.2. Okay, so that's hundredth, which is 2 decimal places. This is tenth, which is 1. And remember, when you're doing your rounding, we don't cascade. So in this case, 3.15, since the next digit is, what I wouldn't do is say, if I rounding to 1,000th, I wouldn't say, well, that's a 5, since that's bigger, and then since that's a 5 here, then this would become a 6. We don't do that. Rounding to the 100th, we look here. To the right is a 4. It becomes 3.15. Rounding to the 10th, we look here. That's a 5. We up this number by 1. So that's a graphical solution to an exponential equation. Okay, here's 363, number 10. Again, solving an exponential equation. This deals with the half-life of cobalt-60. And the first part is, how long does it take for a sample of cobalt-60 to reduce to half its amount? So let's just pick an arbitrary amount of 100, or that could even be a percent. Half of that is 50. And we get 1/2 to the t over 5.3. Let's simplify this before we solve. So 50 divided by 100 is 1/2. That's 1/2 to the t, let me just put that in brackets, to the t over 5.3. And we can see, oh, wait a sec, we've got the same bases. This is really 1/2 to the 1. So we can even solve this algebraically. And so t is equal to 5.3. That was kind of a simple little thing there. So what percent of cobalt-60 will remain in the sample? Well, let's do something that's not in the book, but okay, actually it is. It's part C, 10% of the amount. So what if we go 10% and I start with 100, and I got 1/2 to the t over 5.3. Again, let's divide both sides by 100, so we get 1/10 is equal to 1/2 to the t over 5.3. I don't have the same base now, so I can't solve that way. We do have to solve this graphically. So let's bring in the graphing calculator. Let's go to y equals, go to y equals. We'll clear out what's in there. So here I get 1 divided by 10. And in this one we get bracket 1/2 to the power of bracket x divided by 5.3. And let's just do zoom standard since I had the window way out before. Now 1/10, we're not really going to see that on here, right? So let's take this window and let's take our y values. Y min is 0. Y max is, let's go to 0.5. And I'll leave the scale. So that's my 1/10. Here comes the 1/2 to the t over 5.3. It's going to be somewhere off there, so I'm going to change my x values. So let's take x from 0 to, I don't know, let's go to 50. By 5s. And here we go. We have our intersection, so we'll just let this finish graphing. Second calc, intersect. I move about to the point of intersection, or really close, hit enter 3 times, 1, 2, 3. And we get x, or in this case t, is equal to 17.6. And this is in, what was the half-life? Time. Years, I guess. This is in years. So 17.6 years for the amount of cobalt-60 to be 1/10 of what it was to begin with, right? And we graphed this, y1, this as y2, and we solved for t, or x, as the case may be. Okay, let's continue on. We'll do page 379, number 9, deals with a biologist studying the effects of frog populations, and we are going to be running a regression. So if you turn to page 379, number 9, to see what the numbers are, I'm going to go second plus number 4, clear all lists. To clear my lists out, I'm going to go to y equals. I'm going to clear out everything that I've got in there. And we go to stat. Number 1 is edit. And we're entering the time in years, which is 0, 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. And we'll arrow over. And here we're entering our populations, which are 575, 460, 368, 294, 235, and 188. Okay, we're going to run an exponential regression. So I go stat, arrow over to calc, I arrow up to get to exponential regression, hit enter, go to vars, over to y-vars, hit enter twice. Let's run our exponential regression. We're going to write our equation. Let's round to the hundredths, so 575.23, y equals 575.23, bracket, 0.80 to the x. Now, if I want to answer any questions for this, like what is the population? So if we want to graph this, our window, we know that our initial value, our y-intercept, is 575, right, which was our time at 0, so that matches. If we want to look at a stat plot and our graph, let's do the years, so say 0, maybe we'll go out as far as 10 years with a scale of 1. The population won't drop below 0, and 600 will be our max, and we'll go with 50s. And I can turn on my stat plot here so I can see the points. Now remember to turn that off if you're getting invalid dims. So there are our points. Here is our graph. Now our most accuracy is going to come off the graph. So if I wanted to know what would the population be at 10 or 7 years, let's say, I go second calc, value, x is 7. Okay, and that's going to be more accurate than putting a 7 in here, since the calculator is using its full accuracy. You can see how accurate this is up here. And if we wanted to know how many years will it take for the population to drop, let's say in half. So half, we'll just go 575 divided by 2. And when we hit enter, it will, well, it'll graph that, whatever that works out to. So let's hit graph. Oh, and it looks like it's almost one of our points. We're very close. So second calc, intersect. And let's move. Hit 1, 2, 3. So 3.1 years. So if I were saying to the nearest year, when would it be at least half? It would actually be 4 years, because at 3 years, it will still be slightly greater than half. And so even though this is 3.1, we would have to say that the population will be at least half in 4 years, we would have to go down to the next year, even though then it will be well below half. But to be at least half, more than 3, and the next thing more than 3 is 4 if we go to the nearest year. If we're rounding to the nearest tenth, then, excuse me, after 3.1 years, the population will have reached half of what it was. Now, how is the population decreasing? We can see that since b is less than 1, or between 0 and 1, that this is a decreasing, right, along with the graph 2 going down. It's decreasing at a rate of 1 minus 0.80, which is 0.20, or 20% decrease per year. So what this is saying is we're left with 80% of the population that we had each year. Each subsequent year we'll have 80% of the population, which means that we are decreasing by a rate of 20%. Remember when we do growth, so if I had 1.13, you would go 1.13 minus 1 is 0.13, and this would be a 13% increase, right? So if in another example we had growth, our b value is greater than 1, this is how we would calculate the increase. Okay, let's do a little finance. Page 397, number 14. Denise got a check for $1249.99 from her employer. And she has two options: 7% per annum, compounded annually for 2 years. So our formula is A, simplified form of our formula, P times 1 plus I to the n. So the amount will be $1249.99, 1.07 to the 2. So let's plug that into the calculator. Oops, that's not it. 1249.99 bracket 1.07 to the power of 2. 1431.11. And the second option is 6% compounded monthly. 6% monthly. 6% per annum, also for 2 years. So 1249.99, 1 point, let's do this, 1 plus 0.06 divided by 12 to the power of 24, because we're doing 2 years. So I'm just going to copy this down and go in here and start entering. So 1 plus 0.06 divided by 12 to the power of, and if you like, you can just go 2 times 12 to do the monthly. And we get 1408.94. So this is the option that she should take, as it will get her more money. And that's one of the finance questions. And then one of the last let's take a look at part of number 18 on page 398. This is where we'll end up. So page 398, number 18. We've got Emma borrowing for a car. Let's start at part C. Well, actually, let's start it at A. You need to turn to this. So part A, what did Emma pay for her new car? The initial value will be the number in front, $24,000. The annual depreciation rate, seeing as it's 0.85. Remember, we go 1 minus 0.85, which is 0.15, which is 15%. But the payback question, it's 1.009166667 to the negative n is equal to 0.388888867. And n will be the time in months, and so we want to figure out, okay, how long will it take to pay off? So we're going to have to enter these. So I'm going to clear and go 0.009166667 to the power of negative x, and y2 is 0.3. 1, 2, 3, 4, 5, 6, 7. And we want to see where that matches, so let's set a window. We'll start at 0. Let's go out to 25 by 5s. Oops, x min is 12. Let's go 0. Now, okay, this is months to pay off the loan, and she's paying $300 a month and has to pay off $20,000. So maybe let's go out to 50 by 5s. And our numbers are pretty close, right? That's 0.38, so we're just going to go from 0 to 0.5 by 0.1. And let's try graphing that and see what, whoops. What didn't it like? I did not put a, actually I probably don't need that bracket. So let's try that. So there's my 0.3. I don't think we're quite at enough. So let's try 100. Graph that. Okay, so there's just the beginnings of it. So we're going to go out a little bit further than 100. Doesn't look like we have much further to go. Let's try 125. And here we go. I think we should get a good value here. So second calc, intersect. Need to move till I'm about there. Actually, no, I'm going to move along this curve. There we go. And hit enter 3 times. 1, 2, 3. And we get 103.5. So that will be 104 months. Well, actually, let's use the 103.5. So the total amount, she's spending 300 a month. It'll be 300 times 103.5. So her total payments, 300 times 103.5 are $31,050, 31050. She borrowed $20,000 from the bank, and so the interest will be 11,000. That's a 5 there. 11050. So we take the total amounts of payments minus the amount she borrowed is the total amount of interest that she paid. Okay, and that's pretty much review. Any questions that are in the book are fair game. This was just some examples of some of them, so be prepared to do any of this kind of stuff. And good luck on the test on Tuesday.